All right, for question 6, it says, suppose the temperature T at the point XYZ, and here T is measured in degrees Celsius, is given by the function T of XYZ is equal to x squared times z squared. Find the average temperature over the portion of the cone z squared, which is equal to x squared plus y squared, where z varies from 1 to 2. And we recognize this surface, of course, from problem 4, right, in part C, we found the area of this surface. All right, so here's the parameterization. Again, this just comes from the table. Now v is just the z coordinate, so that's going to vary from 1 to 2, and u is varying from 0 to 2 pi. And so now for the differential surface area element, ds, again, we can just take that from the table. It's square root of 2 times v dA. And then to evaluate our temperature function along this surface, right, along this portion of the cone, well, in the last example, we were able to manipulate the sphere equation to make this evaluation a little simpler. Here, there's not really a simplification possible because we need x squared times z squared. But in any event, it's not terribly hard. We're just going to set x equal to v cosine u and z equal to v. And so we'll get v cos u quantity squared times v squared, and that will give us v to the fourth times cos squared u. All right, so now to find the average temperature, we want to compute the surface integral of the temperature function over this portion of the cone, and then we're going to divide by the area of this surface. And fortunately, we already computed that in problem 4C. So here's the calculation. We're going to do 1 over 3 pi times the square root of 2. And then for the surface integral of the temperature function, okay, well, T evaluated along this portion of the cone is v to the fourth times cos squared u. And then here's your ds, right? It's root 2 times v, and then du dv, and we have the appropriate bounds set up there. Okay, so pretty straightforward integral. For the cos squared, you want to use the identity that cos squared is 1 plus cos 2u all over 2. And when you compute that out, you end up getting 3.5 degrees Celsius for the average temperature over this portion of the cone. All right, that's going to do it. Thanks so much.